So Jonathan is a particle physicist. He explores deep connections between the smallest scales in nature and the largest scales in nature. He grew up in California. He studied physics and mathematics at Harvard and at Cambridge, and he received his Ph.D. from Stanford. He joined the faculty here in 2002 and was appointed a full professor and Chancellor's Fellow in 2006. That's really fast. And he's continued to sort of skyrocket in his trajectory since then. And to be honest, I would not be here if it wasn't for Jonathan, so I'm really happy he's here. Not only did he help recruit me, but honestly, the fact that he was here was one of the main reasons I was like, this must be a very serious place if Jonathan Feng is at this place. And it's true. I mean, he's a big deal. He's a fellow of the American Physical Society and the American Association for the Advancement of Science. He serves on all kinds of boards for national and international organizations about shaping the future of particle physics. His research has been supported by the National Science Foundation, Sloan Foundation, Guggenheim, Heising-Simons, and the Simons Foundation. So pretty much everybody wants to support this guy and put their name on him. I mean, it's a big deal. He's doing really, really important stuff. And by the way, this is him on the set of The Big Bang Theory. So he's also influencing popular culture in lots of different ways. So anyway, we're real proud to have him here, and I think you'll really enjoy the talk. Jonathan.
So let me start off by talking a bit about the dark universe. I'm going to eventually talk about an experiment that is led by UC Irvine and has made tremendous progress in the last few years. But of course, trying to give you a bit of a motivation, let me start with the big picture. And by big, I mean big, okay? The universe. But first, let me start in a place that might seem completely off topic. How many of you remember your graduation speaker? Right, that's what I expected. Okay, that's a one hand go up back there. Probably then none of you graduated from Kenyon College in 2005. Is that true? Yeah, fantastic prediction, thank you. I went way out on a limb there. And the reason I say that is because in 2005, David Foster Wallace, one of the last 50 years, one of the most famous novelists, gave a commencement speech called This is Water, which some consider one of the best ever. If you type in best graduation speech ever, you will undoubtedly see this speech. And he begins with a story. Two young fish are swimming along, and they happen to meet an older fish swimming the other way. Okay? The older fish says, "Morning, boys, how's the water?" And then the two young fish swim on, and then eventually one says, "What the hell is water?" And what David Foster Wallace is trying to get across here is, I mean, it's an incredible speech. I urge you to go see it and hear it, is that one of the difficulties we have is understanding our very environment. We take for granted certain things, and maybe one of the most important jobs in education, and I would say also research, is to understand just where we are now. What is the environment that we live in? In other words, to be like this fish and get out of the water and realize that there was water all around you. Now you might think that, okay, well, fish are kind of stupid, and we're not like that. But actually, that's not at all true. In fact, we are exactly like the fish. We are actually surrounded by a sea of stuff, and we don't even know it's there. And this stuff is actually dark matter. And we can see evidence for this in a number of ways, but one of the classic great ways, and especially for visualizing it, is shown here, where we have two galaxies, okay? And in a second, I'll start the video, and they'll spin around each other. And what I want you to do is look at them and tell me if you can figure out what the difference is in the way that they spin. Where are we? Oh, there we are, okay. Okay, here we go. So they look pretty similar, but they're not exactly similar. Okay, so there it goes. Everyone get a good look at that? So what's the difference? Anyone?
Speed.
Rotation speed. Okay, but rotation speed of the whole thing or just parts of it? Let me try one more time, see if we can get this up here. Just look very carefully. Well, no. Okay. Yeah, one's tighter, sort of. Okay. If you look, you'll see that the insides actually are rotating at about the same rate, okay? But the outsides are very, very different. In this case, they're actually going quite fast around on the outskirts, and here they're going very, very slow, okay? So this has been now basically done in real life. People have looked at how galaxies rotate on themselves. And we can make a prediction based on what we see. We see a bunch of stars, right, in a galaxy. We know stars gravitationally pull on things, and that leads to certain orbital speeds. And to make a long and beautiful story short, what we expect is to see something like this. We expect to see the stars on the outside moving slowly, but what we see is actually this, okay? And this is now true of every single galaxy that's ever been looked at. And basically, what it tells you is that there is something in here that we can't see, that's not shining, that's not bright, but is nevertheless pulling gravitationally on the stuff on the outside. Otherwise, there would be no way this stuff could go around that fast without just flying off to infinity. Okay, so that's just what these things are called, galactic rotation curves. And the stars on the outskirts are traveling too fast to be held in their orbits by the gravitational pull of what you can see. And there must be more matter that we cannot see. And this is the essential evidence for dark matter that was provided by Vera Rubin and others working through the 70s and 80s. Here's a picture of her, one of the great heroes of the field, and also with a fantastic local connection here, because as you might know, one of our most distinguished members in this school is Professor of Mathematics, Carl Rubin, who sometimes comes to these too. Yeah, right there. So that's Carl Rubin, Vera Rubin's son. So this work and now many other pieces of evidence have now basically confirmed this work, that there is such a thing as dark matter, and we just can't see it. So the bottom line is, and of course, it kills me. I hope you all understand in a breakfast talk, it just kills the person talking to not go on and on for 4 hours, right? You know that. But it just kills me to skip over this. But the bottom line is that we now know that the stars we see are actually just islands in an ocean of invisible dark matter. So this is what you think a galaxy is, but it's not. It's more like this, where the dark matter has been artificially colored blue, but that stuff here is just this little piece of it, and it's sitting in this giant ocean of dark matter. And the important thing to realize is not just that it's out there. Okay, it's not like this is some astrophysical problem of the galaxy and not us. In typical dark matter theories, the standard, most basic, most sort of conventional theories we have of dark matter, here on Earth, in every coffee cup, everyone has a coffee cup, there is one dark matter particle. It's passing through at a very high rate, 1 million kilometers per hour, and has a tiny mass of 10 to the minus 22 grams. But if you froze the universe right now, you would find that there are that many dark matter particles in this room. Every coffee cup size volume has one in it. Okay? So we literally are like those fish. We are swimming in a sea of dark matter. We just don't know what this stuff is. If you put this together with a lot of other data, we now know that the elements of the periodic table, which you remember from junior high or high school days, and we're very proud of this table, right? We've figured all about hydrogen and helium all the way down, all through all these elements. That whole body of knowledge is a fantastic description, but of only 5% of the universe. So if you think of the universe as a pie, this periodic table fits in here, this little wedge. And there's 27% of the universe that's dark matter, and an even bigger part of the pie is dark energy. But the bottom line is 95% of the universe is stuff that's still out there to be discovered. And if we want to know where we came from, I'm speaking cosmologically, or where we're going, what's the fate of the universe, or basically just what is our place in the world, we need to find out what this dark universe is made of, because it's basically controlling the universe, and we are but just a little 5% smudge on top of the universe. Okay, so that's basically setting up the motivation. We now know that there are particles out there that we don't know anything about, and we now want to go find them. So that then puts us not in astronomy, but in physics, because this is sort of the goal of particle physics, to be able to understand the basic building blocks of the universe. So let me give you a brief history of particle physics. So in the last century, we have been tremendously successful in discovering new particles and deepening understanding of the laws of nature and the contents of the universe. And this is a very nice, compact summary of all this progress and work. These are now all the fundamental particles we know about. We have like ups and down quarks here, which combined will make the proton and the neutron. Some leptons, like the electron out here, which of course whiz around, that make an atom. We have other ones, and we have the Higgs boson, which got a lot of play because it was just recently discovered. But this has been, a fantastic story in science. If you go back, most of the particles in this chart were discovered by tools that are called particle accelerators and colliders. These are the workhorse tools, sort of the, reflex reaction. If you tell a particle physicist, let's find something, the reflex reaction is go build a collider. Okay, that's what you do. How did this come about? Well, in the 1930s, this person, E.O. Lawrence, working up the state a bit in Berkeley, made a cyclotron which accelerated particles to higher velocities and energies. So here's one of the first ones that was made. As you see, it fits in your palm. And I still remember as a little kid growing up near Berkeley, going to the Lawrence Hall of Science and seeing that cyclotron, which I think is no longer on display there. But it's just amazing, this little thing you can hold in your hand. That first cyclotron was small, but soon people realized if they made bigger ones, they could get higher energies, which allowed heavier particles to be produced and then discovered. Okay? And so it led to this sort of like an arms race of various labs building bigger and bigger accelerators and colliders. The latest realization of this vision of Lawrence is the LHC in Geneva, the Large Hadron Collider. And so here it is. It's outlined in yellow here. It's actually physically 100 meters under the ground. But you get a sense of the size. So this is Geneva Airport right here. Here's the runway for Geneva Airport. Here are the Alps on the back. Here's Lake Geneva. And this thing is 27 kilometers around, the LHC, going through the French and Swiss countryside. Now, that is a huge achievement. And then on top of that, there are accelerator detectors put at various places where the protons are meant to collide. And so one ring goes this way, one ring goes that way, and every so often they are meant to collide. And around those collision points, you have big giant detectors, especially ATLAS and CMS are famous ones that are looking for new particles. But this thing is now able to collide protons at 99.999999% the speed of light. Plus or minus a 9. I can't guarantee I got all the 9s in there. As I mentioned, there's huge detectors put around the collision points. This is one of them, the ATLAS detector, which is the one actually a number of fantastic colleagues of ours work on, ATLAS detector. And it's enormous. Okay, so this is taken apart so you can kind of see the inside, but this gives you a feel for how big it is. Here's a person standing here. And so this is a 6-story tall building size detector. And that's because you need to have lots of instruments to understand what's coming out when the collisions happen. So that is real big science. Okay, so let me just step aside and just say, how big is big science now? So just to remind you if you don't know. So the size is big. The colliders are the size of cities, right? They go around tens of kilometers, and the detectors are the size of buildings. The time scale is long. The LHC was actually conceived in the 1980s. It was constructed from 98 to 08 and has been running since 2008 with periodic shutdowns to upgrade and fix equipment. But we're talking about a project that has taken roughly 30 years now, and it's not even done. The budget, it's pretty expensive. The cost of constructing the LHC and the various experiments was roughly $10 billion. The operations budget of CERN, the host laboratory, is about $1 billion per year, or roughly 1 coffee per year per EU citizen. So when I say it's expensive, of course, it depends who you're talking to. But how much is science worth? The director of CERN, Fabiola Giannotti, who's an Italian, says, look, it's only 1 coffee per year per EU citizen. And in Northern Europe, that coffee tastes horrible anyway. So what kind of a sacrifice is that, right? So, okay, maybe it's not so much. But it's still $1 billion per year, okay? And then how many people does it take to launch something like this? The answer is many, okay? What do I mean by many? So here is, from one of the CMS papers recently, an author list. And it's in little tiny microfont, so you can't even really see it in the back especially. But if you were up front, you would notice that it's alphabetized not by person or by institute, but by country, starting with Armenia, and we've only gotten down to Bulgaria right here, okay? So that's not the whole author list. There's this, okay? So there's more authors, there's more authors. Finally, at this point, we get to the end. So 15 pages of authors, 4,000 collaborators from 230 institutions in 51 countries. That's what it takes to do something like this. Okay, so what's the current status of the LHC? So the biggest recent news is the discovery of the Higgs boson, which came in 2012. That completed that beautiful chart sort of all the fundamental particles, and it was an amazing achievement. Okay, so far there's been no other evidence for new particles like the dark matter that we would be looking for. The LHC is currently in what's called long shutdown 2. And so here's a graph of the year going along here. And then the blue curve is the total amount of luminosity, or basically the amount of data being collected. And we are right here right now in this blue long shutdown period where, of course, no data is being collected, so it's flat. And then in 2021, we will get out of that and start climbing again, taking data, stopping, taking data, stopping, et cetera. So you see that we're not even halfway through. We're here, especially in terms of the amount of data, because it ramps up. And so it's an open question. Will we discover new particles like dark matter or not? This is something of a contentious issue. People like me who are quite optimistic think that there's still plenty of ways to go. Others would say, look, if we haven't seen a hint of one at this point, the likelihood of seeing something for real, with a real compelling discovery, is pretty small at this point. Either way, an obvious question to ask is what other approaches can enhance the prospects for discovering new particles, given that we still have a bunch of ways to go. Instead of continuing on with our standard search techniques, maybe there's some smart thing we can do that will improve our prospects for finding dark matter and other new particles. Okay, so for that, we go back to the drawing board. So we wanted to step back, clear our minds, and really think about this question anew, and just start from the very basics. So let's think, we want to find a new particle. What properties could it have? Well, first it has a mass. It has some mass. Here I've written particle physics units, MeV, GeV, and TeV, but you can think of this as the electron mass, the proton mass, and so the Higgs boson mass, okay, something like that. And then there's also the interaction strength. Basically, how much does it communicate with us? How strongly does it talk to us? And order 1 is sort of the way most particles that we know about, the electron, the proton, and stuff do. But we could imagine weaker and weaker interaction strengths. Particle colliders basically shine a spotlight on this map of possible new particles from the upper left corner. So things that are light are easy to find. Things that interact strongly are easy to find. And so the light comes in from this corner, but of course it gets dimmer and dimmer as we go down. So up here are things that are already discovered. So like the electron sits right here, and of course we discovered that in 1895, so that was easy. Almost all the particles that we know about protons and things are all up in this area. Okay. Down here are things that are basically impossible to discover, at least at a collider, because they're either very heavy, well, they're both very heavy and kind of weakly interacting, and so they're very hard to find. And so if you just look at this, all the action takes place on this diagonal. Here we have strongly interacting heavy particles. Okay, they're very heavy, so you need giant machines to make them and see them, but at least they're strongly interacting, and so you can have a shot at them. And this has been then the traditional target of big science. Okay, that's what all this accelerator technology has been used for. We get bigger and bigger machines, and we look for things like the Higgs boson, but also supersymmetry and extra dimensions and things like that. All these would go in this category. And we see that that really is the legacy of E.O. Lawrence. We basically start with E.O. Lawrence down here and just crank our way up along this axis, trying to get bigger and bigger colliders. But you also see, now that we're back at the very beginning, we can open our minds to realize that although the completely dominating paradigm, dominating way to do physics for the last century almost, is not the only way to go, right? Because there's a little gap here. There's also weakly interacting light particles on this diagonal. And these are weakly interacting, so hard to find, but they're very light, and so you can make a lot of things that might produce them, and so you might be able to find things that way. What we're going to see is that this is now a hot topic in particle physics, and particularly, it's a new target for small experiments. You don't need $10 billion in 30 years. You can do smaller things and actually look for things down here. And here at UCI, it's important to mention that if I had to call this another axis, I would call that the Fred Reinus axis, because that's exactly what he did. Neutrinos are down here. They're not hard to find because they're heavy, they're incredibly light, but they're very weakly interacting, and that's what made them so hard to find. But in some sense, the field has kind of rediscovered Fred Reinus's genius and has started thinking, hey, maybe we should go down this way and see what's around here. Now, that whole story I gave you has been become a hot topic for a number of reasons, but one is because it turns out that as we're looking for dark matter, we've also opened our eyes to this idea that dark matter might not just be a single isolated particle. It might actually be part of a dark sector. Okay? And so the picture that people have been playing with and thinking about more recently is that there's the visible sector, namely quarks and electrons and photons and all the things that we know about. There's a dark sector, which has to have dark matter in it. That's the whole point of the dark sector. But it might have a lot of other stuff in here also. It might have its own forces. It might have other matter particles that are not dark matter. And what it turns out with, if you go through a lot of theoretical work, is that when you have this setup, generically what you'll find is that there will be a portal particle. There's a particle that actually communicates between the visible and the dark sectors. And that has become a very interesting target particle to look for, because it would provide a glimpse of this dark sector, but also because just generically what it turns out to happen is that this particle is exactly a light, weakly interacting particle. So there are now many thousands of papers written about portal particles, which are all in that little corner of that plane that I showed you. And so now all of a sudden, when you look down there, you're probing lots of people's favorite ideas about what dark matter and dark sectors could be. And this is a little hard to explain in detail, but let me just give you a flavor. It turns out if you ask how much of dark matter is left over from the early universe, you can put that on this plane too. And it turns out that particles that are up here actually give too little to be dark matter. They're not good dark matter candidates. The ones down here are actually too much to be dark matter. They would have had so much dark matter the universe would have closed back on itself, and that's not allowed. And actually, this diagonal is interesting, not just because it's where we could look, but also it's the place where you have just the right amount of dark matter. And this sort of realization was worked on with a fantastic postdoc here, Jason Kumar, about 10 years ago, but it's really kind of solidified our thinking because it provides now a cosmological basis to also look on this diagonal, and in particular, to look down here. Okay, so now we have I'm zooming in little by little to the actual topic, and the topic is then weakly interacting light particles. We have this many motivations to look for these things. How can we find them? So we need to then ask, what are their properties? So they're weakly interacting. Let me assume an interaction strength of like 10 to the minus 5. Okay, so you can think of like electrons having charge -1, protons charge +1. These things have like a charge equivalent of 10 to the minus 5. So they're very almost neutral, but not totally. Okay, and let's say they have a mass between the electron's mass and the proton's mass, just to give some sort of rough numbers. So what do we know about these things? Well, they are not bent by electric and magnetic fields. They're so weakly charged that you can put a big giant magnet there and they'll just go straight. Okay, they just don't curve. They don't get influenced at all by electromagnetism. They also do not interact in matter. James mentioned that neutrinos can pass through a light year of lead without interacting. It's the same thing with these things. Okay, they do not hit things. They, for the most part, they just keep going. However, they do, in many cases, decay, for example, to electrons and positrons. Okay, so they will eventually just decay spontaneously to stuff that actually you can see, electrons and positrons. But it takes a while because they're very weakly interacting, so this decay length is extended by that. And typically they travel hundreds of meters. And the other important thing is they are mainly produced in the glancing collisions at the LHC. So protons come in up and down this axis here, and these new particles typically just go right back down the axis. They go right back down the proton beam axis. They don't come out here in the black arrows. That's very rare. Okay? So that's what we know about these particles if they exist. That is an absolute nightmare scenario for the LHC detectors. Why? Because first, they do not interact in matter. Okay, how do you see anything? You see it because it interacts in matter. It hits something, and you see that collision. Okay? Second of all, they do decay, but they go hundreds of meters. So this thing, as big as it is 30 meters. This thing goes like out here, and then finally decays to something you can see, but by then it's gone. And so you have no chance of seeing that. And last, they are produced mainly in glancing collisions. So they are produced along this same beam line. That's exactly where there's a big hole in the detector, because you need to let the protons come in. So the protons come in, and then all the good stuff we're looking for goes straight back out the hole that the protons came in at. Okay? So this billion-dollar detector is in some sense perfectly built to not see these particles. So that then leads to the work I want to tell you about, which is called FASER. So about 2 years ago, I, with 3 absolutely fantastic postdocs, Ifta Galan, Felix Kling, and Sebastian Trojanowski, were thinking about this whole problem with the LHC. And we asked, can we cover the blind spot of existing detectors? Can we, fix this problem that all the good stuff is going out through this blind spot in the detector? So your first naive answer is, oh, yeah, this is a great idea. We'll just put a detector right here, and we'll see that stuff. Well, yeah, you just put a detector where the proton beams are coming through, so you just stopped all the collisions. You basically ruined the entire collider, right? That's not going to work. However, our target particles do not interact. They travel straight for a long time, as I just talked about. We can therefore place the detectors on the line of sight a few hundred meters away. And at that point, the LHC will curve. So I'm saying, go down this way for a few hundred meters out to here somewhere. Eventually, of course, the beam of protons curves because we know the LHC is a circle. It's actually more like an octagon. But anyway, it's a circle. And so at some point, all the beams will curve away. But our particles will just keep going straight because, as I said, they don't interact and they go straight. All the other particles that could have gone that way will get stuck in concrete and stuff like that. They'll get sort of stopped, but our signal particles will be seen. After hundreds of meters, the particles we're looking for will decay, and we can look for the decay products like electrons and positrons. Those are very strongly interacting things that we can actually see. And the new particles, as I mentioned, are extremely collimated, so this red indication here actually doesn't even do that justice. On this scale, they would all be pointing exactly in the same direction. But it turns out if you go 100 meters away, this beam of particles has only spread out by about this much. Okay, so it's like a piece of paper will catch much of the flux of these particles coming down the beam line. And so what that means is that you can build a small, because you only need a piece of paper size thing, inexpensive, because it's only small, detector placed in the very forward region, way up here. That's what it's called, a few hundred meters downstream. And that could actually be the best way to look for these light, weakly interacting particles. Okay, so we realized that. That was fantastic. Then we went and did what anyone do, went to Google and typed in, okay, where can we put this thing in the CERN campus? So, okay, this thing will pop up if you Google LHC. And there's a lot of straight segments out here, but down here there's all sorts of junk. Not junk, it's the stuff that actually makes this thing work, but there's all sorts of other structure down here, okay? If you zoom in there, you get this. And here's the Atlas detector here, and this thing is the LHC beamline. But on top of it, there's this black circle, which is the SPS, which is basically the feeder to the LHC. And you see that there's a tunnel here which connects the SPS to the LHC. Right there is got to be a point where particles coming straight out of here are going to just go right into that side tunnel because the beam will have curved away, but the straight line of sight direction will be right in that little tunnel there. And that's, of course, a big deal because if you go to the people at CERN and tell them, I want you to spend, lots of money and lots of time digging big, giant, dusty things next to your wonderful Large Hadron Collider, they'll tell you to go away. But if you tell them, there's already a tunnel right there, sitting there, that exists, they'll say, oh. They won't necessarily approve it, but they'll say, oh. So here's the picture from above. Okay, here's maybe a little more clear. Here's Atlas, and the LHC goes like this. Straight particles will go straight and then go right into here, and there's this side tunnel, TI-12. If you then go down 100 meters and take a look at what's going on there, this is the view you see as you're looking west. Okay, standing here and looking that way. You'll see here's the LHC with the protons going at this incredibly close to the speed of light here. But here's the side tunnel. And the idea here is that the LHC beamline then carries the visible sector stuff, namely protons, but possibly, if there are new particles, the dark sector particles come right through here, where there's, at the moment, no detector. And so the proposal is then to put something there and look for that. So I have a little video. Hopefully this can give you a better idea of what we're doing here. So just so you orient you, this is Atlas. Okay, and so we're going to swoop in and see how a particle would go from Atlas to the phasor detector. So we swoop in and go through Atlas, and then our particle just goes straight into this side tunnel. And this is what the side tunnel would look like. Okay, did that make sense, everyone? Okay. Okay, so at this point, we get really excited. And what do you do when you get excited in particle physics? You start trying to figure out a good name for your experiment. And you need to make it an acronym. But you don't have to actually make it a good acronym. You can just pick any letters you want, because that's just what we do. And so we called it the forward search experiment. And we called it FASER, F-A-S-E-R, okay? And why do we call it FASER? Well, we thought the acronym recalls another marvelous instrument that harnessed highly collimated particles and was used to explore strange new worlds. And so it's that kind of phasor, but not with a PH, but with an F. And then we came up with a nice logo. After the initial proposal, we did a lot of subsequent work, also a lot of other people did too, and found out that this phasor actually has the potential to discover a whole bunch of different kinds of new particles that people have been looking for, including these portal particles I mentioned that go by the names of dark photons, dark Higgs bosons, sterile neutrinos, but also axion-like particles, and then even new forces can be discovered in this way. And so there's kind of a list of possible kinds of things, and the check marks mean that phasor or phasor 2 can actually see these things. One of the most exciting things about this is that because we're looking at it a totally new way, unlike the existing detectors, we have shown that a discovery is actually possible even with just the first week of running of the LHC in 2021. So the standard thing we do is we write papers where we explore this big parameter space and we figure out what our experiment can do relative to everyone else's proposals and existing constraints. But the bottom line is that, well, there's several bottom lines. One is we can't do everything, okay? I should be clear. It's quite possible we'll build this and see nothing, right? But there are parts of parameter space, even after 1 week of running, where we would discover stuff that no one else could. And so what I'm saying is that after LS2, long shutdown 2, stops and we start running, even that first trickle of data, in this case, might actually discover dark particles. And of course, we got a long way to go. If we just keep running this thing, we'll get 200 times more data than that by the end of 2023. And if we upgrade a little bit, by the end, we might actually get 1 million times more sensitivity. Okay, so that's what we want to do. Now, of course, you have to try to construct this thing. So the timeline was that, as I mentioned, with these 3 great postdocs, we wrote this first theory paper in September 2017. We kind of thought this is such a great idea, someone just decided to build it now. Sat around, waited. Nobody said, hey, I want to devote the rest of my life to doing that thing you mentioned. And so it took a while. One of the first fun things that happened was that in November, we got support from the 2 most famous living physicists. And so You guys know who those are? These guys. So if you go to the Big Bang Theory, episode 9, Seeders 11, the Bitcoin entanglement, you will find on the whiteboards a beautiful photo, or a whiteboard diagram showing phasor here, and even its motivations in terms of making dark photons. So that was fantastically fun, and I got to go and be the geek of the week on the Big Bang set and stuff like that. That was a lot of good stuff. But there's a huge process, and I don't want to go through the details, but just give you a feeling that we've been working hard. You know, first you have to submit a letter of intent to CERN saying you want to do this. We had great help from existing collaborations who basically lent us spare parts that they had, so that reduced the cost and the time. The CERN said, great, nice letter of intent, submit us a technical proposal. A couple of months later, we come back with a technical proposal. Of course, the whole time we're looking for funding. We were very fortunate to get $1 million grants from the Heising Simons and Simons Foundations, who are wonderful. And the way they work is, you know, if they think it's exciting, you get the money like in a few months, unlike the NSF, which is, you know, come back in 5 years. Then in March, just earlier this year, we got fully approved by the CERN Research Board, and they actually supported us with all the infrastructure costs. And we had our first collaboration meeting a few months ago, and we are now actually building this experiment. It's got a very strict deadline. By May 2020, that machine is going to get cooled down, and they're going to start running beams. So if we don't have our detector down there by May 2020, we've just missed the boat, and we'll just have to wait. And so there's a huge, looming deadline that we have to meet. But we're very excited that it's all up to us. The funding is there, the approval's there. This is a photo of us at our first collaboration meeting. It's not 2 people, but this is a tiny, tiny collaboration relative to the 4,000 in the big experiments. This is the current collaboration now. We've now got up to 48 collaborators in 19 institutions in 8 countries. And so here are some of the countries. We got Switzerland, Germany, Italy, Israel, Japan, China, and of course the US. And at the UCI, we have a team here who's just working on it, including undergraduate and graduate students. Absolutely fantastic people. People that have won like Best Student of the Year in both junior and senior classes. Postdoctoral scholars, these people are amazing. Every year we get 400 applications for our one postdoctoral spot, and these people come out at the top. Contracts and grants, as you can imagine, building a collaboration of this sort, especially across 8 national boundaries, writing MOUs, getting all the contracts written, sub-awards out, it's a huge nightmare. And so Alice and Laura, Grace Park, Shelley Scallon, and Chris Sepulveda in various contracts and grants offices here on campus have just been incredibly helpful, helping us to navigate all this. And then principal investigators, Dave Casper is an experimental particle physicist here, and he has done an incredible amount of work. He was actually the first experimentalist on the project. So that's the people working on at UCI right now. But of course, if there's more funding here, we'd be happy to take more people and get more work done. The detector looks like this. This is, of course, a drawing. Okay, we're hoping that we will realize this in real life soon. But it basically, it has a lot of parts. Okay, the particles come in from here, and they go through magnets, which are these things that have these little studs on them, which help bend the tracks and allow us to see that there's 2, like a positron and an electron track, and not just one. And then we have an electromagnetic calorimeter in the back. We have scintillators to allow us to trigger, to allow us to say, hey, something's happening, record all this data. And then there's all sorts of other stuff, cables, cooling, electronics, crates to keep all the data and things like that. Basically, the tunnel that we had at the very beginning looked like this, okay, this empty tunnel that wasn't being used. And we've got to get it to look like that in about 8 months. It turns out that the beam of particles comes through this tunnel, but a little low. So we actually have to dig a small trench here, not a giant tunnel, but a small trench. But then we would put the detector in that little trench. And so these are some photos just from a few weeks ago. So this is how this area looked. the CERN support staff were awesome, just started dismantling all this unnecessary stuff, air ducts and wires and stuff, cleaned it all up, and so now it looks like that, ready for digging this trench here. That'll be done in the beginning of next year. Stairs were added. To get to this place, you have to go down, a tunnel, a shaft, and then you have to walk 500 meters, and then you have to go over the LHC. So the going over the LHC is the part that nobody wants you to do on your own because, you break it and there goes $10 billion. So they installed stairs, it's called a Passerelle, I guess, in French. And so now this is how you get over to our side. And then installed this sort of plastic covering to contain the dust and everything as the excavation goes on in there. What we're looking for is we have basically this detector staring in this one direction, and we're looking for positrons and electrons to come out of a wall, basically, okay? This is a totally spectacular signal. Two extremely high energy, oppositely charged tracks, like a positron and electron, that would be the decay of this dark portal particle. And we're looking for it to sort of start here, then show up and be tracked here, and then show up in the calorimeter. This is an incredibly quiet place because we're 5 football fields away from where people thought all the action was. And so it's a very quiet place with very low background, low radioactivity, and things like that. This is a tracking layer that we've just finished. So there's 9 tracking layers that are in this detector that record the tracks of charged particles as they come through. And this is a very interesting story. This is composed of 8 different modules, 2 by 4. And these modules actually were borrowed from Atlas. Atlas has 3,000 of these things. And when they built Atlas, they made 300 extras just to swap in spare parts. Turns out it worked great, so they never used their 300 parts. And so we said, can we have 80 of them? And they said, sure. And so they just gave us the parts. And that's what you can do with a small little experiment. You can just basically live off the goodwill of the big people. And so we actually got 120 of these in the end, and we're busily assembling them into these things. Last thing I want to say is that turns out FASER, although we're looking for dark sector particles, dark matter, we can actually do neutrino physics. It turns out that, neutrinos are copiously produced at the LHC. Okay? Everyone knows that they're there, but no one has actually detected one because they do this thing of going a light year without interacting. It turns out that if you really want to detect a neutrino from the LHC, where would you put a detector? You would put it where FASER is going to be anyway, because the most energetic neutrinos are the ones that come straight down the beam pipe, and the most energetic ones are the ones that are most likely to interact. And so it turns out that we kind of knew this was going on, but fortuitously, FASER is in the right location to actually do neutrino physics. And we have 0 in the world so far from colliders, but by the end of 2023, we have detected 20,000 of them in our little tiny, box. And we will study their properties at the highest human-made energies ever recorded, which is, I think, a wonderful tie-in to, their having been discovered at the UCI, or by Rhinus. Okay, so the conclusion is that 95% of the universe is waiting to be discovered. That is a huge thing, but relatively recently, we found out that fast, small, cheap experiments can actually provide world-leading sensitivities and perhaps our first glimpse of the dark universe. In this case of FASER, fast, small, and cheap has meant 18 months from the theory paper to the beginning of construction, not 30 years. If it's on a tabletop, a kind of big table, but a tabletop, okay, 5 meters long. And it costs $2 million for all the hardware, not billions. We're still hoping for a little bit more for operations, but to get the thing off the ground, we have all we need to actually purchase all the equipment and put it together. The data taking will begin in 2021 with neutrino measurements, which are guaranteed because we know neutrinos exist. So we are going to make the best measurements of neutrinos at high energies ever. And then with also discovery prospects for proposed new particles with possibly a glimpse into the dark universe. And there's a little animation made, and then also more information at this webpage. So thank you very much. Yeah, so you picked up on something really important, and I think I said it, but it didn't probably say it well. What we're actually looking for in many cases, actually the portal particle. So the dark matter sits over here in some sector, and as you say, that thing better be awfully stable, because it survived for the whole time of the universe. And that's not going to decay to visible stuff. But the portal particle could do that, would do that. And it'll be unstable and can decay, actually, in some cases, both ways. So it could decay to visible stuff, but also to dark matter. And so kind of in the best possible world, I mean, I think to be totally fair, we're actually looking mostly for portal particles, but those might actually give us a glimpse of the dark matter, because we actually might see these particles, and then by various detailed measurements, be able to figure out that they're decaying to dark matter. And then we would see sort of indirectly dark matter. So in the end of the day, the best we can do is first get this portal particle. I mean, that's something that we're guaranteed to get if it's sitting in certain places in parameter space. But the dark matter part, detailed measurement of the dark matter, that would be like a second stage. Yeah, so there are other accelerators, and there are other experiments being done. But for us, CERN is by far the best because it's the highest energy. It turns out if you want to get these things launched hundreds of meters, you need very high energy so that they survive that distance. If there's lower energy, of course, you can try to put your detector closer, but then you start getting more and more background, and it becomes harder and harder to distinguish the signal from the background. So by far, the best place for us was CERN. But it's an important point that this field has now attracted lots of competition. I think we're actually sort of leading the pack because we've got this fast track schedule and we're all ready to go. But many other places are trying to think of new ways to build this at other accelerator facilities in the US or Japan or other places at CERN. Well, so in many ways, it's just a fortuitous coincidence of a whole bunch of things. One is that the theories that we're thinking about naturally lead to decay lengths of about that scale. So that's kind of where you'd want to put it anyway. But the other reason is there's this tunnel there. And that just, I mean, all of a sudden, when you see that tunnel, your attention just focuses on it. Because all of a sudden, this thing goes from being this giant 20-year project to let's do this tomorrow. I mean, that's kind of how you think. Well, that's very interesting. So the neutrinos that we will guarantee detect that obviously exist are so-called active neutrinos, and those are not portal particles. Because actually, portal particles typically have no standard model interactions whatsoever, not even the weak ones that neutrinos have. There are, however, variants of the active neutrinos called sterile neutrinos. Those actually have no interactions, and they are actually a classic portal particle. And so, people here, Kev Abazagian is one of the world's leading experts on this. We have other experts, Mu-Chun Chen, who are fantastic neutrino experts. But the sterile neutrino has been around for a long time. But recently, it's been sort of brought into this fold of a portal particle and thought of this way. And that's a very classic particle, and we can actually look for those also in FASER.
Okay, well, thank you very much, Jonathan, for a great talk. Let's thank him again.
Thanks, James. Thank you all.